Hi, I'm Rafik Mitry, and in this episode we're focusing on automotive applications built and deployed on NXP hardware. Today we're looking at a function that is present in every vehicle on the road: rear lighting control. It covers stop lights, turn signals, fog lights, hazard indication, and fault management. While it may appear straightforward, the underlying implementation requires a robust state machine capable of handling multiple conditions simultaneously, with the reliability and determinism that automotive applications demand. We'll look at how this application is designed in Simulink and deployed directly onto production-grade automotive hardware. Before we get into the details, let me show you what this looks like in action. On the bench here is the physical vehicle model with the actual rear lights, connected to the Freedom Automotive board underneath. On the screen next to me is the driving simulation running in Simulink. Now I'll take control of the vehicle and start driving. The rear lights on the physical model are responding in real time to the simulation state. Now watch what happens when the rear sensor detects an obstacle. The sensor threshold is crossed, the logic transitions to the braking state, the stop lights assert, which is visible right here on the physical model. The same state machine running on the S32K312, responding to a live simulation event in real time. Now let me walk you through how this is built. The hardware platform for this demo is the Freedom-A-S32K312, part of NXP's Freedom Automotive development platform. At its core is the S32K312 microcontroller, an ARM Cortex-M7 running at up to 120 MHz, AEC Q100 qualified with ISO 26262 functional safety support. The peripheral set includes ScanFD, LIN, and FlexIO. What accelerates the development process here is the model-based design. Using MATLAB and Simulink, provided by MathWorks, the application logic is fully modeled and validated at the system level. NXP's model-based design toolbox provides a library of Simulink blocks that map directly to the S32K312's peripherals. Hardware configuration, including pins, clocks, and peripheral setup, is handled through NXP's S32 Design Studio, allowing the engineer to focus on application behavior instead of low-level initialization. The application-generated code from Simulink can be imported into S32 Design Studio, enabling step-by-step execution and debugging on target. This reduces integration effort and minimizes late-stage changes. The application we're looking at is Rear Lights Controller. It receives commands over the CAN bus, processes them through a control logic layer, and drives the corresponding hardware outputs. In Simulink, the model is structured around three subsystems: command receiving, control logic, and hardware output. Each subsystem has a clear responsibility, and together they form a clean, traceable path from the bus signal to the physical lights. CAN communication is managed using MathWorks Vehicle Network Toolbox. The message database is defined in a standard DBC file, and the toolbox handles the decoding and passing of those signals directly into the NXP blocks that interface with the hardware. The decision-making logic lives in a state flow chart. At any given moment, the system is in one of four states: idle, braking, or one of two fault states. It monitors the brake command coming from the CAN bus and the health status of the lighting system, and transitions between those states accordingly. When the driver brakes, the system moves to the braking state, and the stop lights come on. When released, it returns to idle. If a fault is detected, the system captures it, flags it, and holds that information for diagnostics. This application sits within a much broader system. In a full vehicle network, the Freedom board operates as one end node among many, communicating over CAN and LIN to zone controllers, connecting via Ethernet to the central compute platform, and feeding into cloud connectivity through the network gateway. What is significant is that every node in that architecture can follow the same development approach: NXP silicon, model-based design, and automatic code generation. The same methodology that produced this rear lights application scales to any function in the vehicle, with the same tools and the same path to production. Today we looked at a rear lights control application built with Simulink and NXP's model-based design toolbox, deployed to the Freedom-A-S32K312. And this was done from model to embedded target without manual coding. For more information, visit mauser.com.